Let us now discuss an example for the graphical solution of linear programming. And we have the problem. A company manufactures two models of a product, which we call the regular model and the enhanced model. Two resources, A and B, are needed for the manufacturing of units of this product. And the detailed resource requirements are given in the following table. We have uh, the regular model. It will need three units of resource A and two units of resource B to be able to create one model in the or one unit for the regular model. On the other hand, the enhanced model will be needing 4 units of resource A and 7 units of resource B for one unit of an enhanced model. So suppose further that the company has 650 units of resource A and 500 units of resource B available per week, and that the net profits for selling of the regular model and enhanced model are given respectively as $5 and $7 per unit. So what are the optimal weekly production levels for these models? So if you will consider the problem, look at the last statement given. This is our goal. And the goal of the problem will tell you where you will obtain what you call your objective function. That is where you will get your objective function. And reading again the statement for a while. For this one, what are the optimal weekly production levels for these two models? So in other words, we would like to look at what production levels will we create for both models so that we will now have the optimal solution. But what are we optimizing in the problem? So if you will again go back to the problem, what we would like to optimize will now be our net profit. Net profit based from these production levels that we will be creating. So in other words, if you will read and understand this section again, our objective function here is to maximize the profit, and let's say we can call the profit as P. So the profit will be based from the number of production levels that we will be doing per week per model. So we have two models. We have the regular model and we have the enhanced model. So we can say here now that we can let X be the number of units produced for our regular model. We can just have that as Rm. And then we can have Y be the number of units produced for our enhanced model. Of course, this will now be on a weekly basis. Okay? So for both, this will now be on a weekly basis. And because of that, we are now ready to write down our objective function. And what will be our objective function? Our objective function is to, again, maximize P, and how do we compute the product or the product? How do we compute the profit? So the profit will depend on how many units we produce for the regular model and the enhanced model. So the number of units for the regular model is X. The number of units produced for the enhanced model is Y. How do we get the net profit? Isn't it that you will find here that the profit per unit is given? So 5 for the regular model, $7 for the enhanced model. Therefore, profit the profit function shall now be given by the equation P is equal to $5 ang profit per unit of the regular model times the number of regular models produced plus $7 per unit for the enhanced model multiplied by the number of units produced for the enhanced model. So what we are trying to look for is what should be the best combination? How many number of regular models will be produced and how many enhanced model will be produced so that we get the maximum or the largest or the biggest profit. But of course, we don't just substitute values for x and y here. We have what we call our constraints. So this objective function will now be subject to the following constraints. And what are the constraints? So when we say constraints, these are the conditions. So let's go back to the problem. So what are the constraints? So according to our statement here, to be able to produce one regular model, we need 3 units of resource A and we need 2 units of resource B. So at the same time, the enhanced model, to be able to produce 1 unit of an enhanced model, we need 4 units of resource A and we need 3 units of resource B. So what else do we know? What else do we know? The company only has 650 units of resource A and 500 units of resource B available per week. Resource A, how many are available for resource A per week? 650 and then 500. 650 and then 500. So per week we have 650 units available and 500 units available for resource B, okay, per week. Therefore, how do we now establish our uh, constraints? So remember, our variables are x and y. X is the number of units produced for the regular model and y is the number of units produced for the enhanced model. Regular model X, enhanced model Y. Okay, so how do we now use these following constraints? Okay, looking at this condition that for resource A, there are only 650 units available per week. So that's the maximum. Of course, this resource A, 3 units will go to the regular model, 4 units will go to the enhanced model. Okay, which means one constraint that we can have there will be 3 times x, the number of regular models that we produce, plus 4 times the number of units we produce for the enhanced model, and there are 650 units available per week. That's the maximum. So it should be less than or equal because this is 650 is the maximum. And then based now from resource B, there are 500 units available. 2 units will be used for a regular model. 3 units will be used in producing an enhanced model. Therefore, this will now give us a constraint that will now be 2x plus 3y is less than or equal to 500. Again, we have a maximum of 500 units available per week. And then we have our non-negativity constraints, x greater or equal to 0, because we need to produce, we cannot produce negative number of regular model. We cannot also produce negative number of enhanced model. Therefore, y must be greater or equal to 0. Okay, so we already have our objective function, and then we have our constraints. The next thing that we will do is to graph our constraints. And how do we do again the graph of a constraint? So we begin by looking at each statement here. So for the first one, if x is 0, what will be y? So let's convert this first to an equality. Okay? Let's convert this first to an equality. So if x is 0, what will now be our y? 650 divided by 4, which gives us 162. If you will calculate this, 162.5. And then if y is 0, x will now be 650 divided by 3, which is 216.67. While for the second equation, if x is 0, or converting this again to an equation, if x is 0, y will be 500 divided by 3, which will give us 166.67. If y is 0, our x will now be 250. So let's plot those points on our Cartesian plane. So we have 160, 216, 167, and 250. So how do we now divide this? So let's say we have for 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Then I'll use 50. 1, 2, 3, 4, 1, 2, 3, 4. Okay, let's just pick our Cartesian plane. So this is the y-axis. This is our x-axis. I'm using intervals of 50. Okay. That's 100, 150, 200, and 250. So please forgive my handwriting. It's so difficult to write using this tablet. Okay, the first one. X is 0, y is 162.5. X is 0, 162.5. 150, 162.5 is somewhere here. There. And then, if y is 0 to 16. If y is 0 to 16. Somewhere here. I'm just approximating. Okay. Then let's now join those points together. Joining those points together. Let me extend this line. And then let's change the color. Okay. So that will be the equation of the first line. But if you would like to see the inequality less than or equal, so as we have mentioned earlier, if in the earlier lecture, if it will now be less than or equal, we consider the section below. Okay, this section below. Okay, this entire section. Let's not shade the entire section anymore, just to make our graph neat. And the second one, if x is 0, 166, that's 67. If x is 0, 166, 166, that's 67, 166. X is 0, 166 by 67. Okay, somewhere here also. What was the point earlier? X is 0, 162, so it must be higher. 167. It must be a little higher. Let me just exaggerate it. There. And the other one, y is 0, 250. Y is 0, x is 250. It must be this point here. And let's connect those points together. Let's insert a line connecting now those 2 points together. And where is the other one? 250. Okay. There we go. So if I'll extend this, okay. So there you have it. And then let's look at the uh, it's less than or equal, so it must be going down here, going down, going down, going down, going down. Okay, I don't know if our graph is that accurate. And then our non-negativity constraints, x is greater or equal to 0. We have this. And then y greater or equal to 0. We have this part here. Okay, so where is the common region? So if you will look at our diagram, it seems that the common region is from this point here going to this point here, and then, oops, sorry, and then this entire thing here. Therefore, our feasible region is this part here. Okay, this entire thing here. Okay, this entire thing here. Maybe we can use this. Let's shade it. There. That seems to be the feasible region, but I don't know if I have graphed the lines accurately, because the point of intersection of the two seems to be outside the first quadrant. Okay, but anyway, let's check that. Let's check that. Maybe we can go back here and let's compute the intersection of the two lines. So let me copy the equations first. Let me insert another slide here, and let's compute the intersection. Let's just check. I'm just checking because I'm not sure if our graph there is accurate. So we have 3x plus 4y, converting it to an equation, and then we have 2x plus 3y equals 500, equation 1. Equation 2. Let's just check if the intersection is located in the first quadrant. So let's eliminate x. Equation 1, I can multiply it by 2 to make it 6x plus 8y equals 1,300. And then equation 2 be multiplied by 3, giving us 6x plus 9y equals 1,500. So I subtract, because they have the same signs. I subtract one equation from the other. I proceed to addition. This will cancel out. This is minus y equals minus 200. Therefore, y is 200. If y is 200, let's substitute it in equation 2. Let's say we have 2x plus 3 times 200 equals 500. Therefore, we have 2x equals, this is 600, transpose it, 500 minus 600 is negative 100. Divide both sides by 2, it's negative 50. Okay, so we have negative 50, 200. So you will find here that the intersection is not in the first quadrant. Not in the first quadrant. Since this is not in the first quadrant, we cannot use this point of intersection because we cannot produce negative units for the first material or for the first type, which is, how do you call that? Regular, right? It's a regular model. So it means our graph is correct. The point of intersection is outside the first quadrant. Okay, so our corner points will now be this point here, another point here, and our origin. Okay, and it's the it's the graph of what line? The first one, right? The first one. So that is 0, 162.5, 0. So let me label the points. Let me label the points so that we'll not get lost. Let's call this as corner point 1. Let's call this as corner point 2. And let's call this as corner point 3. And based from our analysis earlier, corner point 1 is the x-intercept. X-intercept. X-intercept, this one, y is 0. 216.67, 0. 216, 216.67, 216.67, and then 0. And then corner point 2 is this, 0, 162.5, 0, 0, 162.5. And then, of course, corner point 3 is the origin. Okay, there you have it. Now, how do we determine our optimal solution? So to determine the optimal solution, what we will do is we now create a table. Okay, we now create a table. So we have our corner points, and then we have our objective function p. What's our objective function p? We have 5x plus 4y. And then we have corner point 1, corner point 2, corner point 3. Corner point 3 is the origin. Corner point 1 and 2, 216, that's 670. 216, 216, that's 67. 0, and then this is 0. What's that again? 162.5. 162.5. Okay, what will we do with these points? So for each point that we have, we will compute the resulting profit. So for the first one, x is 216.67. So 5 times 216.67. This gives us 1,083.35. Of course, that's in dollars, plus 0 because 4 times y 0. And then for the next one, this time x is 0. y is 162.5. So 4 times 162.5 gives us 650. And then for the last one, p is 0. Okay, so comparing now the entries that we have here, you will find that this has the largest value. This has the largest value. Therefore, if that's the largest value, our conclusion will now be, therefore, the optimal solution, okay, therefore, the optimal solution will be x is 216.67, and then the maximum profit, so y is 0, and then the maximum profit is 1083.30. Of course, this is in dollars. So that will now be our maximum profit, and this will now be the number of units produced for our X. Now, in this case, since you might be wondering, but the result is a decimal. Okay, so if if the production must be in whole numbers, then we can round this off. Okay, so if it will now be since this is speaking about regular model and this is a product, right? So if it's a product, it must be in terms of full numbers. Therefore, we can revise this. Okay, so technically this is the optimal solution, but if we will follow the production procedure, so we have to round this down. So the nearest whole number that we have for x will be 216. Y would still be 0. Therefore, we can also recompute the profit. That will now become 5 times 216, which will now be 1080. Okay? So we're just doing a recomputation of the values because we are considering that our production must be a whole number. So we have to drop this part here to have a whole number answer. Therefore, this will now be our optimal solution. So that's an example. That's an example of a linear programming problem using the graphical